All right. So yeah, chapter 9, we have been talking about the one sample t-test, the one sample t, which is what this thing is. This thing is right here. Let's go to the example. Yeah, right here is the example. So here is a little data set. And I mentioned last time, this is, pretend that this is a data set where there's 5 people, and each of these scores is a person's score on a quiz or a test that has 10 questions. And each of the 10 questions is true or false. So in a true or false test, you have a 50% chance of guessing correctly. And I guess there's a couple things here. When we add up these 5 scores and then divide by 5, we get the sample mean, M, equals 6. But we also have this 5. This represents, going to our formula, that 5 right there represents this, mu, the population mean, which I've mentioned that in the one sample t-test, the population mean will oftentimes be inferred. It'll be a hypothetical population mean, or will be inferred based on the rules of probability theory. So how did we get this number 5? Why is that our mu here? How are we inferring this? What is the basic mathematical computation or rule of probability theory that we're using to get this number 5 right here? Anyone have any idea?
The best score that you can get would be 10. So you're just taking the very middle, which would be 5 because it's 10 divided by 2.
Mm-hmm. Yeah, 10 divided by 2, or 10 times 50%. There's a 50% chance of getting any given question right. There's 10 total questions. So if you're guessing on every single question, you're going to get 50% of the questions correct. 50% of 10 is 5. So this number 5 represents chance performance. If you're guessing on every question, that's what you expect participants, the amount of correct answers they'll get will be 5. The amount of correct answers people actually got was 6. Chance performance is 5. And so what we would do is we calculate a one sample t-test, a one sample t, which we did last time, 2.236. And what this number tells you is, are these two numbers significantly different from each other? Is the sample mean of 6, is it significantly different than chance performance of 5? If people were guessing on every problem, you would expect them to get 5. Is 6 significantly different than 5? And then we're not going to do it again right now, but then you'd use your t-table, given the degrees of freedom, which would be 4, and the amount of tails and whatever your alpha value is. And then if it turns out that this t-value is in your critical region, you will reject the null hypothesis. If the t-value is not in the critical region, you will accept the null hypothesis. That's one sample t. That was just some review. Now we're going to talk about repeated measures t, also known as within subjects t, or paired samples t. So really there's 3 names for this thing. So I'll say them all again. Repeated measures t-test, within subjects t-test, or paired samples t-test. They're all synonymous. Those things all mean the same thing. In my head, I think though the word I use probably the most is within subjects t-test. Though I think your textbook calls it paired samples t-test, but they all mean the same thing, and different sources use different words. So you kind of have to get comfortable with the fact that there are multiple names for this one t-test. Repeated measures, within subjects, and paired samples all mean the same thing. So what is this thing? Repeated measures design is one of the common one of the common components that all repeated measures, paired samples, within subjects t-test all have a repeated measures design. A repeated measures design, once again, is when each participant contributes a score for all of the conditions in the study. So if we have a study with 2 conditions and I'm a participant in that study, I'm going to contribute a score to condition 1, and I'm going to contribute a score to condition 2, and everyone would be the same. All the participants would contribute a score to condition 1, and they would contribute a score to condition 2. That's a within subjects design, or a repeated measures design. Yeah, and so I'm contributing 2 separate scores, one for each condition. And that's it. And so I have an example, I think, coming up. Oh yeah, no, first we're going to talk about the formulas and then we'll talk about the examples. Okay, so here is the one sample t equation right here. And then here's the repeated measures t equation right here. So this is what we just dealt with. Like last week when we were doing one sample t, this is what we are using. This week when we're calculating repeated measures t, this is what we're going to be using. And structurally, these two t equations are basically virtually identical. And you can see the big difference here is that this is the exact same as this, except we have all these subscript d's right here, d, 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 d. So all these things being the same, except now we have this component, these things called difference scores, which are really important in repeated measures t-test. So structurally, these t's are exactly the same, but it says it right here. The one sample t is based on x values. You do these calculations based on x values. This t right here is calculated based on difference scores. And so I'll teach you, or I'll show you what difference scores are, and then we'll also have a little bit of practice calculating different scores today to help you understand what those things are. So a difference score, here is kind of the basic definition of a difference score right here. Can someone mute that microphone, whoever that is? It sounds like... Okay, so D means difference score. And as I mentioned, if there's two conditions, you're going to have a score for condition 2 and a score for condition 1. And so the D equals the score for condition 2 minus the score for condition 1. And you do that for all of the participants. Or you could do the opposite way. It's actually mathematically equivalent. You could also do D equals the score for condition 1 minus the score for condition 2. It doesn't matter which of these two that you use right here, as long as you are consistent. So when you're calculating the difference score for your participants, do all of them using this formula right here, x2 minus x1, or use this formula right here for all of the participants, x1 minus x2. You'll get the same end result. It doesn't actually matter which of these two formulas you use. You just have to be consistent. You can't start for participant 1 using this formula, and then for participant 2 use this formula, and then go back to participant 3 using this one. Do all your participants with this, or all of your participants with this. And what that does is that will give you the difference scores for each of your participants, and I will show you an example of that in a second. We're also going to be calculating this thing, and I'll show you an example of this as well, called the sample mean difference score, or the mean of the difference scores, M sub D. And what we're going to do is we're going to add up all of the difference scores for all of our participants, and then we're going to divide by N, which is the number of participants. So let me show you that. Now is when we have the example right here. So here is an example of a data set, a small data set with 4 participants. So N equals 4. A, B, C, and D. Those are the 4 people. Those are the 4 subjects, 4 participants. We also have 2 conditions called condition 1 and condition 2. And then you can see this column here called D. And these are the difference scores right here. And so we have this number 4 here, which we took for participant A, subject A. We took their score in condition 2, 14 minus 10 equals 4. Then we go to participant 2, 13 minus 15 equals negative 2. 15 minus 12 equals 3. 12 minus 11 equals 1. So that's how we calculate the difference scores. We could have gone the other way as long as we're consistent. We could have gone 1 minus 2, 1 minus 2, 1 minus 2, 1 minus 2. We could have done that. We would have gotten different numbers there, but the end result when we're calculating t, as long as you're consistent with doing the same direction for every single person, the end result of all of this process will be the same. So here, though, we did x2 minus x1 for all of these participants to get our 4Ds. Just be consistent and you'll be fine. So those are our 4Ds. Now we want to calculate the mean difference score, M sub D, right here. And so the way we do that is we take each of these 4Ds and we add them together, and then we divide by 4. And just so we know why we're doing this, once again, this is coming from this formula right here. The mean of the difference scores equals the sum of all of the difference scores, we calculated 4 of them, divided by the amount of different scores, which is 4. So we add up these 4 things, 4 plus minus 2 plus 3 plus 1. When you do that, you get 6 right there. And then we're dividing by 4 because there's, the sample size is 4. We have 4 subjects, 4 different scores. 6 divided by 4 equals 1.5. So for this little example right here, the sample mean difference score is 1.5. Any questions or comments about how to calculate difference scores and the sample mean difference score? All right, moving on. Okay, so here are the formulas that we're going to be using to calculate repeated measures t. And then I'll give you an example, and I'll actually calculate repeated measures t for you using that example. So once again, this is structurally the identical to one sample t, except we have all these d's here, which mean difference score. One nice thing about t when you're doing a repeated measures t is you always know what the mu sub d is going to be. By definition, when you're doing a repeated measures t-test, the mu sub d will always be 0. This comes from the null hypothesis, which I'll show you very shortly. Mu sub d will always equal 0, which is nice because basically that means we don't care about this at all. We can basically pretend that this doesn't exist because it's 0. Anything minus 0 is just whatever that thing was. So really what we care about is m sub d, which we just calculated for an example. And we'll calculate it for another example. M sub d, that's going to be whatever the mean of the different scores is, that's the numerator of our t. The denominator will be the standard deviation, sample standard deviation of the different scores divided by the square root of n. So we'll have to learn how to calculate sample standard deviation of the different scores, which is right here. S sub d, S sub d, and basically this is the standard, this is the standard deviation equation, sample standard deviation equation we've been using for a long time now, except instead of this being an x value, this is now a d, and instead of this just being an m, this is m sub d, meaning it's the sample mean difference score. But we're still dividing by n minus 1 in the denominator, taking the square root. So this is a typical standard deviation equation, except now we're putting in d's instead of x's. And then the standard deviation goes in right there. This whole thing at the bottom is estimated standard error of the different scores, which is what this stands for, SMD. SM, earlier in the chapter, means estimated standard error. We're just adding that D there, estimated standard error of the different score. This is just the denominator right here. Standard deviation of the different score divided by n, standard deviation of the different score divided by n right there. Okay. So here is what I was just referring to, the degrees of freedom and the null hypothesis for any repeated measures t-test. The degrees of freedom will always just be the sample size minus 1. Sample size minus 1. And then the null hypothesis for repeated measures t-test will always be the same. We will never do a repeated measures t-test where the null hypothesis is anything other than this. The null hypothesis for a repeated measures t-test will always be mu sub d equals 0. The reason this is because you remember what a null hypothesis is it's basically saying there's no difference between the conditions. If we did a study where there was no difference between condition 1 and condition 2, when we calculate those difference scores, we should get, if there's no difference between the two conditions, 0. If there's no difference between the two conditions, then when we take the mean difference score, we should get 0. So the null hypothesis says the mean average of all of those difference scores should be 0, meaning there's no difference between our two conditions. So the null hypothesis for repeated measures t-test is always mu sub d equals 0. It will never change. It will always be this, no matter what. And the research hypothesis is, therefore, mu sub d is not 0, which means mu sub d is greater than 1 or mu sub d is less than 1. Okay, so here's an actual example. We're going to calculate a repeated measures t. So the first thing that we're going to do is we're going to calculate the d's. The sample size here is 10. So n equals 10. This is an example where it's just like the example from earlier in the chapter where infants were looking at attractive and unattractive faces, but to mix things up a little bit, I made it so that instead of the infants looking for 20 total seconds on each trial, they were looking at 10 total seconds on each trial. And so once again, there was two faces they could be looking at. One was on each trial, there's a computer screen. One of the faces of the computer screen was attractive. One of them was unattractive. They're looking at the computer screen for 10 total seconds. At any given point in time, they're always looking at either the attractive or the unattractive face, depending on which one their eyes are closer to. We measure the amount of seconds that the infants spend looking at each of the two faces, and that's what the data are showing here. And what we want to do first is calculate all of the difference scores. And so remember, when you're calculating the difference scores, you can either go unattractive minus attractive or attractive minus unattractive. It doesn't matter. You just need to be consistent. Me personally, I like to avoid negative signs. I like to, if possible, I like to avoid the minus signs. And so I'm going to take attractive minus unattractive. That's how I'm going to do it here. And so make sure that you understand. I'm going to type in these answers here. Make sure that you're following along so you understand how I'm getting these answers. 5 minus 5 equals 0. 7 minus 3 equals 4. 6 minus 4 equals 2. And then you notice these are all 6 minus 4 down there. 2, 2, 2, 2, 2, 2, and 2. So those are our difference scores. We've now calculated the 10 different scores. 0, 4, and then the rest are all 2s by taking attractive minus unattractive and doing that for all 10 participants. Questions or comments about how I got those difference scores? Okay. So here's the same data set again. There's the same difference scores that we just calculated. 0, 4, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, right there. And so now what we want to do is we have those difference scores and we want to calculate repeated measures t. So remembering repeated measures t is this thing. It's basically the same as the one sample t, except now everything's based on these different scores instead of on the raw x values or the raw scores. I already mentioned also, because of the null hypothesis, mu sub d equals 0. So we don't have to worry about this ever in a repeated measures t-test. This will always, in a repeated measures t-test, this will always just be 0. So we'll never have to care about this. All we really care about is this thing right here and this thing, the denominator right here. So the first thing we want to calculate for this data set that we're working on is the sample mean difference score. We've calculated all the difference scores. Now we need to calculate the mean of all of those different scores. That's what we're going to do first. So here are all the difference scores. Let's add them all up and then divide by the number of difference scores. Remember the mean, or the equation for this is the sum of d's divided by the sample size, n. The sum of d divided by n. So if we add up all of these d's, 4 plus 2, 6, 8, 10, 12, 14, 16, 18, 20. 20 divided by 10 equals 2. So the mean difference score equals 2 right here. And are there any questions as to how I calculated the mean difference score? The sum of the d's divided by n. 20 divided by 10 equals 2 right here. So now we know this thing. This thing is 2. This thing is 0. So we already know that our numerator is going to be the number 2. We still have to calculate our denominator, though. That is, we still have to calculate the estimated standard error, which is this whole thing. In order to do that, in order to calculate the estimated standard error, we have to first calculate the standard deviation of the difference scores. Take each d minus the mean of the d's, so that's minus 2. Each d minus 2, square that number, and then do that for all of the participants and add them together. Then divide by n minus 1 and take the square root of that ratio.
Dr. Rosenthal?
Yeah.
For the n, it has the subscript d, but do you do anything special to it?
Nope. Okay. All that means is you can either count the amount of participants or you can count the number of d's. But you notice how there's 10 participants and there's also 10 d's. The reason why the D is helpful is because you want to make sure that you're not counting the number of scores. The number of scores would be 20. That is not the sample size for repeated measures t-test is not the number of scores. It is the number of Ds. The number of Ds is 10. So good question. There's nothing special. You could still think of that in the sample size as being the number of people or the number of different scores. In either case, the number is 10 here. Okay, so now, once again, we want to calculate the sample standard deviation of the different scores. And so I just showed you the formula. I remind you the way we're doing that is we're taking each different score. These are the Ds. These are the different scores right here. Each different score minus the mean of the different scores, 2. You subtract those two numbers. You square it. You do that for all 10 of the different scores. And then you divide by n minus 1, 9, and then you take the square root. So first, let's do taking the D's minus the M sub D's and squaring and then adding those all together. So 0 right here minus 2. That's what I'm showing you here. 0 minus 2, that equals -2. -2 squared equals +4, which is this thing right here. So here's a different score right here. 4 minus 2. 4 minus 2 equals 2. And we have it right here. 4 minus 2 equals 2. 2 squared equals 4. Now, D, for this one, D equals 2. 2 minus 2 equals 0. You can see it here. 2 minus 2 equals 0. 0 squared is 0. And because the rest of these numbers are 2, the rest of these squared different scores using D equals 0 as well. So these are all of the squared different scores right here using D. Squared different scores using D right here. And if looking at our formula, we just found out, we just took each D minus the M sub D. We did that 10 times. Now we have to add the sum right here. We have to add those 10 things together, which is what this column is doing right here. 4 plus 4 plus 0, 0, 0, all those zeros equals 8. So this is the sum of the squared different scores right here. This is the numerator part of our standard deviation equation. The denominator is going to be what? Does anyone know what our denominator will be? What will this thing be? We know that the numerator is going to be 8. Anyone know what the denominator is going to be?
9.
It is 9. Good. So I think we've plugged that in. Yeah, right here. Here's where I plugged in some of the numbers into our formulas. So the standard deviation, the sample standard deviation of the different scores, 8, which comes directly from here. This is the numerator, 8. The sum of squared of the different scores is 8, divided by 10 minus 1, which is 9, divided by n minus 1, which is 9. And then you take the square root. I don't remember what 8 divided by 9 is off the top of my head, but whatever that number is, when you take the square root of it, this is the answer, 0.9428. And if you can see here is the sample standard deviation of the different scores, 0.9428 right here. So that's our standard deviation. We need to, if you wanted to calculate the estimated standard error, you would just divide this number divided by the square root of 10, which is what you can see right here. The estimated standard error, which is the whole denominator of t, is 0.9428 divided by the square root of 10, which is right here. The numerator we've already talked about. This is the number 2 comes from right here, the m sub d. The 0 right here, u sub d, comes from the null hypothesis. I mentioned this will always be 0, so basically you never really have to worry about it for the repeated measures t-test. The numerator is 2. The denominator is 0.9428 divided by the square root of 10. When you work all the math out, you get 6.708. So now would be the time I'm not going to finish this hypothesis test right now. What we would do, though, is we would take this t and we would compare it to the critical t to determine whether we are in the critical region or not. And we did a lot of practice last week looking up t's on the critical t's on the t-table. Remember, there's 3 things you need to know to look up a critical t on the t-table. You need to know the degrees of freedom, which would be 9 in this case. You need to know the amount of tails, and you need to know the alpha level to look up a critical t on a t-table. We're not going to do that right now because we had a lot of practice. I'll probably do some more examples of those, looking up t-tables Wednesday in class to review one more time for this chapter.
Is this a two-tailed test?
I haven't specified. I will mention that in psychology, like 99.9% of all tests are two-tailed. So if I don't specify whether it's one or two-tailed, assume it's two-tailed because that's the convention in psychology these days is to use two tails. But I haven't specified that at all because right now I don't actually care about finding the critical t. The main goal of today's class is to help you guys know how to calculate the repeated measures t, which is what we just did. We're not going beyond that yet. We're not going to actually use the t-table in today's class. But if I were doing this in real life, yeah, I'd assume that this is a two-tailed test. But we'll come back to the idea of two-tailed and one-tailed one more time in Wednesday's class. Any other questions or comments about repeated measures t? Okay. So we've just calculated one of these things, repeated measures t. Now I want to kind of give you connect the dots a little bit, give you a big picture idea of what's going on with this repeated measures t. And what I mean by that is I want you to understand how this relates to the one sample t-test that we just calculated earlier on in the chapter. It really turns out that these two formulas, they're structurally similar, and sometimes you can actually use both formulas, that is one sample t formula or the repeated measures t formula on the same data set, and they will give you the exact same value. Though you can use, so in other words, you can use the two t's that we've learned in this chapter, one sample t and repeated measures t. There is a specific situation in which you have the choice which one of those to use. You can use either one, and it doesn't matter. They'll both give you the exact same value, and they'll both give you the exact same decision as to whether to reject or accept the null hypothesis. So it's important to kind of understand the big picture of things that are going on here, is to understand what is the situation in which you can use either of these two t's. You can use either repeated measure t or one sample t, and that's described right here. When chance performance can be determined, that chance performance can be determined when you have a repeated measures factor with two levels, and when you add up the scores of each participant in condition 1 and condition 2, it equals a constant value. So I'm going to really emphasize this part. Chance performance can be determined when the score in condition 1 plus the score in condition 2 equals a constant number. For the current example that we're using right now, if you add up the amount of time the baby's looking at the attractive plus the unattractive face, it always equals 10 seconds. Let's verify that. Right here, 5 plus 5 equals 10. 7 plus 3 equals 10. And all these 6 plus 4s equals 10. So this is what I mean by a constant number right here. Because this number is constant right here, we can calculate what chance performance would be. And what I mean by chance performance is if the infants were looking randomly at the two faces, how much time would they spend looking at each face? You tell me, someone tell me. Given that the babies were looking at for 10 seconds and there's two faces, if they were looking randomly at each face, how long would they spend looking at each face on average?
5.
5, yeah, which is the same, same basic rules of probability that we've been using. The total amount of time times the percentage of, divided by 2. There's two things here, 10 divided by 2, or 10 times 50% equals 5. If the babies are looking randomly at the two faces, then they should spend 5 seconds looking at the attractive face, 5 seconds looking at the unattractive face. We are able to calculate that number 5. We are able to calculate chance performance because this score right here plus this score equals 10, and it does so for every single participant. The sum of the two conditions always equals 10 for all the participants, and that is the only situation in which you can calculate chance performance, is when this number is constant over here, when the numbers for both conditions always equals the same for all participants. Then you can calculate chance performance. So going back here, we just calculated repeated measures t. That's what this is right here, repeated measures t. But I'm telling you that because these numbers are all 10, because they're the same, because we can calculate chance performance, We can also calculate a one sample t-test as well. And the one sample t-test will give us the exact same number. That's basically my hypothesis for us, and I'll prove it to you, that given that we're going to calculate one sample t right now, it's going to give us that exact same 6.708 number that we just got when we did the repeated measures t. So let's prove it. So now I'm showing you the same data set, but now down here, this is using the one sample t formula. So these are the formulas that we learned about last week. The previous slide, I was showing you the new formula, repeated measures t. This slide is one sample t. So these are the formulas that we learned about from last week. So right here, we're calculating sample standard deviation using the raw x values, the raw scores. So right here, this number right here we get from taking, well, first off, we need to know how we got the sample mean right here. The sample mean equals 6. The way we got that is we add up all 10 of these scores, 5 plus 7 plus all these 6s. That gives us 60. 60 divided by 10 equals 6. So this is the sample mean of these scores right here. The mu right here, this represents chance performance, 5. If the babies are looking randomly, they should look at each face for 5 seconds. They actually looked at the attractive face for 6 seconds on average. We're going to do a one sample t-test to determine, is this 6 right here significantly different than this 5? That's what the one sample t-test is comparing, is these two numbers. First, we have to calculate the sample standard deviation using the raw x values. 5 minus 6 equals 1 squared, equals 1. 7 minus 6 equals 1 squared. 6 minus 6 equals 0. 0 squared is still 0. And because all the rest of the numbers are 6, 6 minus 6 is always 0. We get a whole bunch of zeros right here. So that's the numerator of our sample standard deviation equation. We have this number 9 right here. Where did this number 9 come from? What is this?
Minus 1.
N minus 1 is correct. This is just the sample size, 10 minus 1. This is the standard deviation equation, sample standard deviation equation we used last week. N minus 1 is the denominator. And so 10 minus 1 equals 9. So we do that 2 divided by 9, we get that ratio, and then we take the square root of whatever that number is, and we get 0.4714. 0.4714 is our sample standard deviation for the attractive faces right here. Please note that when we're doing the one sample t-test, we basically ignore the unattractive condition altogether. When you're doing the one sample, I think we had a technical issue with the internet right there. Was I cutting out verbally? Could you guys having trouble hearing me before I cut out for a long time?
Yes.
Okay, darn. All right. I'll go back and have to repeat things then. How long, I need an estimate. How long was I cut out for? Like a minute?
Yeah, I would say a minute or 2 minutes.
All right, bummer. All right, well, we'll have to go back in time. So let's fix that. Share the screen. All right. You guys can see my screen?
Yeah.
Good. Okay. I want to make sure we'll go back to at least this. This is basically the beginning of calculating the one sample t-test. The sample mean here is 6. And you get that from adding up all of these things right here. These are all the scores in the attractive condition. You add them all up, you get 60 divided by 10 equals the sample mean, which is 6. The mu right here represents chance performance, which is 5. We just talked about that. There's 10 total seconds. If they're looking randomly, they should look at each face for 5 seconds. The one sample t-test is determining whether these two numbers are different. This one sample mean, is it significantly different than the hypothetical population mean of 5? Is 6 significantly different than 5? Please note that for the one sample t-test, we're basically ignoring the unattractive condition. We're not doing any calculations on the unattractive condition. We are only dealing with the attractive condition when we're dealing with the one sample t-test. That's an important thing to note. One sample t-test, you're only dealing with one condition, with half the sample, basically, one sample. So here's how we calculated the sample standard deviation for this example. You're using the x values. 5 minus 6 is 1. 1 squared is 1. 7 minus 6 is 1. 1 squared is 1. 6 minus 6 is 0. 0 squared is 0. And we have a whole bunch of 6's right here. And so we have a whole bunch of zeros right here. So this is the numerator of our sample standard deviation equation. And then this is 9 right here. We got that from n minus 1. 10 minus 1 equals 9. Do the whole thing right here. The sample standard deviation is 0.4714, which you can see right here. So now we can calculate t. Our sample mean is 6. Our hypothetical population mean is 5. Our sample standard deviation we calculated right here is 0.4714. And then our sample size is 10, square root of 10. You do all that, you crunch the numbers, and you get the exact same thing, 6.708, that you would have gotten, that we calculated when we did the repeated measures t. So what we're seeing here is that when you calculate a repeated measures t for a data set, then you will get the same thing that if you calculate a one sample t for the exact same data set, as long as it holds true that these two values equal a constant number. In this case, these two values, this value plus this value always equals 10. Therefore, we can figure out what chance performance is. If we can figure out what chance performance is, we can calculate a one sample t-test. The one sample t-test here gives us the exact same value, 6.708, as we did when we calculated the repeated measures t-test right here. So that's actually all I have planned for today. So you can get out of here. If people have questions, I'll stick around to answer questions. But we'll call it a day there, and we will meet back again Wednesday.